also known by some fools as Euler circuits, but it's not. It's Euler circuits. Euler is how you pronounce this guy's name. An Euler circuit in a graph, remember, is a circuit that is a path which starts and ends at the same place, which uses every edge exactly once. A circuit using each edge exactly once. All right, so for example, something like if this is a graph with just like vertices at all the corners here, this one actually does have an Euler circuit. What we talked about last time was mostly just the question of, here's a graph, does it or does it not have an Euler circuit? This one does. I can draw it. If you like, you can draw it, or you can give labels to all the vertices and then describe what the circuit is by writing out the letters one after another. But anyway, if I start in this point, say, I hope that you can see how you might, there are many ways that you could do this. How about, I'm going to go around here, watch my red dot. I'm going to go around here, come down here, maybe go around the small circle first, and then around the bigger rectangle, and then back home like that. I don't know if you saw that. Doesn't matter. I'm going to draw it. Something like this. An Euler circuit is meant to use every edge once without repeating any edges. You may repeat a vertex, like usually you have to repeat vertices in order for this to work. There we go. That's my Euler circuit. I covered every edge once without repeating any edges and without missing every edge, without missing any edges. All right? Remember, if you're going to draw these like I did, you really should draw your path as, don't draw it right on top of the original edges, and don't make it go right through the vertices, because it's very difficult for me to tell what you mean if you draw it that way. You gotta make it a little sloppy for it to work out nicely. All right, this is the idea behind Euler circuits, and we talked towards the end last time about Euler's theorem. Euler's theorem about Euler circuits. It tells you when an Euler circuit exists and when it doesn't. It said an Euler circuit exists if and only if. That means what I'm about to write is exactly like mathematically equivalent to an Euler circuit existing. If and only if all vertices have even degree. This is Euler's theorem about Euler circuits. All vertices have even degree. That's actually how I knew that this example was going to work out, because if you look at those vertices and try to figure out what their degrees are, the one in the upper left, that's a degree 2. Remember, degree is just how many edges are touching it. That's a 2. That's a 4. This one here has degree 4 because there are 4 edges that go into that vertex. That's a 2, a 2, another 4 here, a 2, a 2, a 2, a 2. Anyway, they're all even, which is why that worked. All right? This is what Euler's theorem about Euler circuits says, that the Euler circuit exists if and only if all the vertices have even degree. So if they all have even degree, then you know there is an Euler circuit. If some of them have odds, if even one of them is an odd degree, that means there can be no Euler circuit. All right? And I hope you remember last time the idea behind why this is true. It's because in an Euler circuit, every vertex has to be visited an even number of times. That's because in a circuit, every vertex, this, like the red line, has to come in, entering, and then exit again. And it might happen once, like this point here. There's one, this red line enters once and exits once. It might happen twice. Here it enters once and exits once and then enters again. So here I have 2 enterings and 2 exits, all right? But anyway, there's always got to be the same number of enterings and exits, which is why those degrees are always going to be even in an Euler circuit, all right? So that's the basic idea behind Euler's theorem about Euler circuits. I hope everybody's feeling good about this. I want to do a bunch more examples today, and also I want to do something a little bit fancier. rather than Euler circuits, we could ask a related question. What about a path which uses every edge but maybe doesn't end up where it started? All right. How can we tell in a graph if that is possible or not? There's a name for that, actually. So this is a related concept. This is unsurprisingly called an Euler path. This is like a Euler circuit in that it uses every edge once with no repeats, but it's not a circuit. It starts at one point and ends at a different point. Okay, so an Euler path, this would be a path, not a circuit. That is, it starts and ends at two different points, all right? A path that is not a circuit, which uses every edge exactly once. All right? There are some graphs which have no Euler circuit, but they do have an Euler path. I got an example. So let's talk briefly about Euler paths. It turns out, like, based on what we already know about Euler circuits, actually, it's not so hard to make some simple observations that let us do the same kind of business, but about Euler paths. So this graph here, first of all, I could ask, does it have an Euler circuit? And in order to answer that question, you would look at the degrees at all of the vertices here. What do you think? Does it have an Euler circuit? That's the same as saying, are all the degrees even? No. Which ones are not even? Yeah, the two. She's giving me the signal. This signal. The two on the middle on the either sides are both. These are degree 3 each, right? Those vertices have 3 edges coming into them. Actually, all the other ones are 2s. But that doesn't matter. Like, as far as if there's an Euler circuit or not, I'm going to say there are some odds. So there's no Euler circuit. Euler circuit requires everything to be even. So there are odds, so there's no Euler circuit. But actually, in this example, there is an Euler path. It is possible to make a path in there which covers every vertex, although it's going to start and end at 2 different points. Check it out. I got to redraw down here. All right, I'm going to cover every edge once, but it's going to start and end at 2 different points. Let's start here. See how I do. I already know how to do this, which is why I was able to begin sort of without hesitation. There are strategies about how to do this. Here we go. I did it. All right, that is an Euler path. I covered every edge once. I said, there we go. I should have said, let's go. I know that's what people say nowadays. That's what the young people say on the Twitch, the streamers. Let's go, dude. So this is an Euler path. All right? That means it uses every edge once without repeating any edges. But it's not a circuit. It starts at one place and ends at a different place. All right? That's an Euler path. Now, how do you know if an Euler path exists or not? Actually, there's a similar, simple trick for deciding whether or not Euler paths exist. Remember, Euler circuits, every vertex has to be even because there's always the same amount of departures and enterings, right? The same amount of times the circuit has to arrive and then leave again. In an Euler path, though, I will point out, it's actually not always the same number of times because, for instance, at my starting point, I have an extra departure. And at my finishing point, I have an extra arrival. That's because they are the starting and the finishing point. So in an Euler path, otherwise everything looks the same. So I'm going to say an Euler, can I just for now say EP for Euler path? An Euler path looks like an Euler circuit, except the start point has an extra, I will say, leaving edge because the one where you start, it actually does depart, and it doesn't come back eventually. I mean, it might come back once, but then it's going to depart again. It doesn't eventually come back to this point at the end. And so this point has sort of an equal number of arrivings and departings, but it has an extra departure, an extra leaving edge. And the end point, for the same reasons, the end point has an extra arriving, right? Because at the end, it arrives but never leaves. So the starting point has an extra leaving edge, and the end point has an extra arriving edge. So as far as the evens and odds goes, what this means is they're all going to be even except for the starting and ending point, which will be odd, right? The starting and ending point each have an extra edge, but all the other ones are still going to be even. So I'm going to say all vertices will be even degree except the start and end, which are odd, right? Because they have one extra edge each. So those two are going to be odds. This is why, in that example I just did, these are all the vertices in this one are 2, except for those 2 on the sides there. And it is not a coincidence that my starting and ending point happened to be the 2 odd ones. Actually, it must be the case that the 2 odds must be the start and the end. It's just not going to work any other way. All right? So this is how you know if there's an Euler path or not. Circuit means they're all even. A path means they're all even except 2 odds. It is pretty easy once you understand. So I'm going to write this as a theorem also. I'm just going to write the stuff that I wrote before combined with the other theorem. So I'm going to say a graph. I'll say there is an Euler circuit. This is what I already wrote. Circuit if and only if all vertices have even degree. There is an Euler path if and only if all of them are even except for 2 odds. All vertices have even degree except for 2 odds, right? This is the rule for existence of Euler circuits or Euler paths. It's very, very simple. You just have to remember, if they're all evens, there's a circuit. If there are 2 odds, there's a path. And in any other situation, there's nothing. You can't do Euler circuits or Euler paths if you have more odds than that. So I will just say parenthetically, if more than 2 odds, then there is no Euler whatever, Euler circuit or path. If there's more than 2 odd vertices in your graph, then there is no Euler circuit or path. All right? This is sort of the full version of Euler's theorem about Euler circuits and Euler paths. All right. Any thoughts about that one? Great. Very simple. Like I was trying to say last time, I really like this theorem just because it takes a concept which on its surface is quite complicated, this existence of Euler circuits or paths, but it boils it down to something which is very, very easy to observe just by looking at the graph. All right. I could ask you about the graph on the quiz today where everybody is connected to the other people in their building. If we that's a disconnected graph, so you wouldn't even think about doing Euler paths. But if we just consider this building here, only our piece of the graph, would you say there's an Euler circuit or an Euler path in that graph? I can tell you're on the right track when you're thinking about this. Is there an Euler circuit or an Euler path? I just said that because the tour walked by, and I wanted to sound encouraging while the tour was walking by. I have no idea if you're on the right track with your thinking about this. Whenever I ask you, is there an Euler circuit or Euler path, you have to think in terms of the degrees, right? The question in your mind should be, are all the degrees even? Or are all of them even except for two odds? Those are the questions. I would say for the graph representing our building here, in which all of us are connected to everyone else in the building, actually I don't know what the degrees are. The degree, like my degree, just happens to be however many other people there are in the building. And that, I suppose it's a 50-50 chance if that's even or not. I don't know. And so if there are an even number of other people in this building, then there would be an Euler circuit, and otherwise there wouldn't. And I think it's not possible to be a path in this case because in our building everybody would have the same degree, so it's not possible to have two odds and the rest be even because we all have the same degree. All right, it's Friday. One interesting question arises here, at least I think it's interesting. What we've dealt with here is, this is the situation if all the vertices have an even degree. This is the scenario if they're all even except for two odds. And then if there's any more than two odds, there's no Euler nothing. I kind of left out one scenario here, which would be, what if there's only one odd vertex in the graph? Then what? That's not addressed by anything that I said here. So what about, what if there's only one odd degree vertex? For example, can I draw an example of a graph with only one degree, one odd? How about, okay, this one is degree 3. The others are all degree 1, so I'm going to try and connect them up. Actually, now this is a 2, that's a 3, that's a 2. Anybody see how I could modify this maybe to make it so that they're all even except for 1? That's what I want. Only one odd. You know, you can increase the degrees by adding more edges. I could add another edge between this 3 and this 2 to turn this 3 into a 4 now. But I guess I turned this into a 3. There's still two odds. Yeah.
Can you make a vertex at the bottom and just have one line going into 3?
Yes?
One edge, yeah.
Yeah. Then this is now a 4 and this is a 1.
Oh.
Yeah, if you try to add more edges to make everything even except for 1, you will notice that you always end up screwing it up. You can change an odd to an even, but that always ends up changing another even to another odd. Actually, this whole thing is a bit of a trick question. This is impossible. It's a fact that no graph can ever have only one odd degree vertex. And there's a name for this. Actually, this is another thing that was discovered by Euler. It's a much more complicated or more sophisticated statement than this. This is not possible to have only one odd. The reason I'll write this as another theorem. This is called Euler's, this actually is kind of the common name for this theorem. Euler's sum of degrees theorem. The sum of degrees theorem. It says in any graph, no matter what, the sum of all the degrees in any graph, the sum of all degrees is even. This is a true fact of every graph. The sum of all the degrees is even. This is not exactly an obvious fact, although there are reasons. It's not so hard to understand why that's true. But just, I will draw a cute little graph here. How about this? This is like a little robot guy. All right? How do you like my cute little robot guy? The sum of all the degrees is even. That's what Euler's sum of degrees theorem says. In this case, the degrees, if I just look real quick here, that's a 3, a 3, a 3, a 3, a 3, a 1, a 2, a 2, a 2, a 3, a 1, a 2. And if you add these numbers together, I should have made this cute robot smaller. I wasn't prepared to actually add all these numbers together. I'm going to get 10 here, 12, 14 from the head part, and then another 10 is 24, 28, 32, 34. I believe you get 36 if you add all the degrees here. So I'm adding up all the degrees. Sum of all degrees in this example is 36, and that's even, and that's not a coincidence. Actually, any graph that you make will always have an even sum of the total degrees. Why is that true? Actually, I can say just in a moment. Why is it true? It's basically because every edge in the graph has two ends. And so when you're adding up all the possible degrees, that's just the total number of how many times an edge touches a vertex. Well, every edge touches two vertices, because that's what an edge is. It goes from one vertex to another. And so that's why when you add all these numbers up, you're going to end up with an even number, because the edges all touch two vertices. In fact, not only can you say it's even, actually this number is actually 2 times the total number of edges. This graph I know has 18 edges without even counting them, because each edge has 2 ends, and that's why when you add up all the ends, you get to 36. All right. Anyway, this is why the sum of degrees theorem is true. The sum of all the degrees must be even. And this is also why it's impossible to have only one odd and the rest even, because then when you add them up, you would end up with an odd, because an odd plus an even is an odd. So anyway, this Euler sum of degrees theorem, the sum of all the degrees is even. So this is why no graph can have one odd, the rest even. Because in that case, then if you were to add up all the numbers, you'd end up with an odd, which is impossible. All right. This is the Euler's sum of degrees theorem. It's important. Actually, it comes up in the real world sometimes. I actually have an interesting story. This, I believe, is a true story, although I have not. I tried to look into this and I was unable to determine the precise dates on which this happened. But this is a true mathematical story involving the National Football League, the NFL. NFL true stories, which has to do with Euler's sum of degrees theorem. It turns out this was important in the NFL once upon a time. So here's the scenario. In the NFL, there was, here I tried to look up the dates for this, but I was unable to do this. But anyway, at one point, so at one time, you will see very quickly how clueless I am about the NFL. I don't know anything about the footballs. I've heard of Brady and Gronkowski, but I don't really know what that means. I know those are people's names. Anyway, at one time, the NFL had 2 conferences, which I believe is still the case, with 13 teams in each. This is no longer the case. I think there are more teams today. But anyway, what they do, like before the season begins, the fat cats who run the NFL decide what the schedule is going to be, right? So this is about the schedule for the NFL in this year. And they decided, they came up with sort of the guidelines for the schedule. They decided that the guidelines said each team will play 14 games, 11 games inside their own conference, and 3 games outside of their own conference. All right. Most of these details don't matter, and it doesn't matter if you know what any of this means. I only barely know what this means. All right. So anyway, they came up with the rules about how they were going to create the schedule. This is like before they actually made the schedule, and then they just like they came up with these rules: 14 games, 11 in conference, 3 outside the conference, and then they just like told some other guy, and they're like, okay, make us a schedule which obeys these properties according to these guidelines. All right, but it turns out actually this is impossible. It doesn't seem impossible. Like, it's not obviously impossible. It doesn't seem like a ridiculous proposal. We have 13 teams in a conference. To say they're each going to play 14 games, 11 in the conference, 3 outside the conference, that's not a stupid idea, but it turns out to be impossible for reasons related to the sum of degrees theorem in a graph. So let's imagine that we turn this into a graph, all right, which is a very natural way to view these games. There's going to be 14 games that are played between these 13 teams. So I would like to imagine a graph of the teams. There's 13 of them, right? The 13 teams. And let's just consider their in-conference games. I actually don't care about the other ones. The 13 teams and 11 in-conference games. All right? So, for example, you're going to have in your graph, I guess, 13 different vertices, right? Each one will be a team. Let's say one of them is the Patriots. I've heard of them. And then they would be connected up to all the other teams which they play a game against, which is not everybody because they're only playing 11 games. All right? So can anybody say how many edges will there be coming out of this one here? You have one edge per game that just connects them to the other people they're playing. 11. Yeah, they're playing 11 games, and so there will be 11 edges here. All right? So each vertex, and this is true of all of them, right? That's how the rules work. So each vertex here has degree 11, right? And there are 13 of them. And so what is the total sum of degrees? I don't imagine the people who invent the NFL schedule also consider the sum of degrees in the graph that they are trying to describe. But actually, in this case, the sum of the degrees, so the total sum of degrees, sorry, my hand moved. The total sum of degrees is, each vertex has 11, and there are 13 of them. So it's really 11 plus 11 plus 11 plus 11, 13 times. In other words, 11 times 13. Because there are 13 vertices, and they each have degree 11. And what's that? It doesn't so much matter. It's odd, though. That's the interesting thing. So in this case, the total sum of the degrees is 143, which is odd. And what is my conclusion? That is impossible. That means this graph cannot exist, which means this schedule, hypothetical schedule, is impossible to actually create. So this graph cannot exist. All right? It means when you are trying to, say, if you are trying to make up the NFL schedule, you can't just make any old rules that you want. There are actually some sort of obscure mathematical considerations that need to be satisfied in order for one of these scheduling guidelines to be possible at all. And I assume there is somebody at the NFL who understands some basic graph theory who can do this. It's not just the NFL. Everybody has to, there's probably people at Fairfield University who make up the athletic schedules, and they have to keep things like this in mind when they're trying to create their schedule for the year. Ask your coaches. I've never actually tried to talk to somebody at the university about this, but all right. Any thoughts about that? Graph theory matters in the real world. All right, anyway, I got some simple examples for you to try. So I am going to draw some graphs. Your job each time will be to tell me if there is or is not an Euler circuit or an Euler path, or just nothing like that is possible. I'm going to draw. How about this? This is like Satan's graph. All right, there's a vertex at each intersection. And in here too. All right, here's another one. This is like the Triforce, but I'm going to, just for fun, put another thing down there. So each intersection of lines, there is a vertex there. And then I got one more. All right, so those are 3 graphs. Your job is, for each one, tell me, is there an Euler circuit or not? Is there an Euler path or not? And if your answer is no, then just say no. If your answer is yes for any of those, then try to draw it in. All right? It's all about the degrees. The tours are going to love this when they see me walking around the room being so nurturing and giving you all individual attention. The moms love that. I know what moms like. It's an important life skill as an adult man. Or as a little kid, I guess. For a path, there has to be 2 odds. But this one with no odds means there is a circuit.
Yeah. One is me. Okay, yeah, I was thinking this is last part. So
Yeah, that's
okay.
part of the graph. But where's your starting point?
I can really start right here. And then I was drawing one. So
Okay.
that was done.
Yeah, so actually, once you finish, just go all the way.
Okay, that makes sense. I'll redo it. Yeah.
And my other comment was,
Yeah.
when you draw your arrows, they have to connect up. Because I can't tell after
Okay.
this one is go down or left.
Okay.
I don't know.
Got it. Right.
Okay. This is a Euler circuit.
No way.
you think there is a Euler whatever, you should try to draw it in. Look at the numbers first. This good. Yeah. You also want to hit these ones.
This one
Yeah, you just say. Good. Yeah, that was good. Is it doing okay? All right.
Let's see.
Yeah, it's a
Are we
little.
supposed to get the pencil down?
Yeah, you gotta cover all. Every edge.
I
Yeah.
got that, I just don't know where
You should cover these like this too.
Oh, right, I meant to go around.
I'll give you another couple minutes and then we'll talk about them. Okay?
Yeah. It can pass it through this, right?
Yes. Yeah, it's gonna have to. All right.
And then,
All right, can we discuss these? I hope you drew the pictures. Maybe you should have drawn them bigger than I did. I can just do that. Right? So think about the degrees, first of all, for all of these. In this picture, if you thought about it, I think you should have decided. These are all degree 4 here. 4 is even, of course, and so this one does have an Euler circuit. Now, I actually happen to know how to draw a star shape like that without repeating any of the edges. So I'm going to maybe start here, and I'm just going to... This is how my mommy taught me when I was a kid to draw a star. Something like this, at least. This should end up covering all the edges of the star part. Now, there are many other ways you could have drawn the edges, but I think this, to me at least, is the most natural way of doing it. Now, I also need to hit the sort of rounded edges that go around the outside, but that's easy enough. I can just go around, right? After all that, I'll go around the outer edge. And that'll do it. Right? Many different ways to make this circuit work, but that's how I did it. Any questions about that one? So this, I didn't say, this one has an Euler circuit, right? Okay. Great. Let's try this one over here. So this one, again, you begin by checking out the degrees. This is a 4, that's a 4, 3, 3, and 2. So I see 2 odds, the rest evens. That means, here's my 2 odds, right? That means this one has an Euler path. And if you recall, the 2 odds are going to have to be the starting point and the ending point. So when you're trying to draw your path in, you better start at one of the 3s, and it's going to end at the other 3. Let's just see how I can do this. Now we're going to talk next time in much more detail about how do you actually decide where to draw the path. But for this example, I think it's not too hard to just kind of make it up as you go along, and hopefully it'll work out. That's how I'm going to play this. So maybe I'll come around this way, like this. I'll come back here. It is okay to revisit a vertex. In fact, you have to, basically, to make this work. You just have to cover every edge one time. And I think I did it. Covered every edge without repeating any. All right? You're going to have to start at one of the 3s and end at the other 3. Any thoughts about that? Probably none of you drew exactly the same path as I did, but that's fine. Yeah?
If it always has 2 odds, should you always see them?
Yeah, if it has 2 odds, you must start at one of the odds and end at the other odd if it's going to work at all. If you decide just because you want to be different to start at an even, it's not going to end up working. You're going to end up having to retrace one of your edges. All right, and this one here, again, look at the degrees. That's a 2, a 3. This is 1, 2, 3, 4, 5. That's a 3. Actually, I can sort of stop now. I see more than 2 odds, which means there is no Euler circuit or Euler path, although I'll fill in the rest of them. Although all you care about is there's more than 2 odds. That's a 4 in the middle. This is a 5. This is a 5. All right, so this has more than 2 odds, so no Euler circuit or path. All right, that's how we do it. Any questions about that? Great. I got a few more like vaguely real-world examples, and then that'll do us for today. I meant to say at the beginning, just a little reminder, we are going to have our test next week. So my plan for Tuesday is to do maybe a little bit of new stuff, which will not be on the test. And then I will have another review sheet like we did last time. And then I would be happy to discuss old examples of things. You want to remember how to do the bonds off, that kind of thing. But anyway, that's the plan for Tuesday. All right. We will have homework due as usual next week, covering this stuff that we're doing right now, plus last time. Okay, couple more vaguely real-world examples. How about, let's think about Mr. Plow again, although this is a different picture. Let's say this is Mr. Plow's neighborhood, like that. And let's say that no, let's say Mr. Plow just doesn't live here. When I had a similar example before, I said like Mr. Plow lives in the middle. I don't want to get into that though. So this my question is, so you think of these as like streets in a little neighborhood. Can Mr. Plow drive each street without repeats? And let's just say, I don't care if he's going to do it in a circuit or in a path. That doesn't really matter to Mr. Plow. He just wants to cover every street without repeating any. Is that possible in this graph? What do you think? You should look first at the degrees, right? That's all that matters in terms of this business about repeating edges. That's a 3, that's a 3, a 2, a 3, a 3. I intend for all these streets to meet there, and a 4. All right. What do you think? Can Mr. Plow drive each street without repeating any? The answer is no, because there are 2 odds. That means there is no Euler nothing. All right, so no. Did I say 2 odds? I meant more than 2 odds, right? More than 2 odds. So we must repeat some. All right. Here's a follow-up question. Mr. Plow's girlfriend is Ms. Road. She builds roads. And she loves Mr. Plow so much, wants to build a new road simply in order to make it possible for Mr. Plow to do his thing in the neighborhood. Can anybody say, is it possible to build a new road somewhere which will enable Mr. Plow to cover every edge without repeats? Ms. Road wants to build a new road to help him. Kind and considerate. So I'm going to just copy this picture again. Anybody see how to do it? Can you add a new road into the picture? What do you think?
You do a line between the 3 and the 3.
Like another diagonal?
Yeah.
Yeah, how about a new diagonal road from this 3 to that 3? I like this idea. This changes the degree here. It used to be 3, but now it's 4 because there's an extra road there. And this one up top used to be 3, but now it's 4. And now this one is possible. So now it has an Euler circuit. Not circuit, it has an Euler path, right? And you can say specifically where the Euler path is going to start and end. Oddly enough, it does not begin on the new road, even though the new road is what makes it possible. The Euler path does not begin on the new road. It begins here at one of the 3s, right? It would start at one of the 3s. Here, let's just draw it in. I think I can do this. Goes down like this. There are many ways to do it as usual, but I'm just drawing one in. There you go. I would make such a good plowman. All right? Show me the streets. I could immediately tell you if there's a good route or not. Now it has an Euler path. All right, that was a vaguely real-world example. I got just briefly 2 more simple examples that are also vaguely real-world. I have a handout because these are kind of big, and I didn't want you to have to copy them down. Again, on the topic of vaguely real-world examples. All right. So what we have here is the standard original Pac-Man layout, and then at the bottom is the basketball court. Let's actually look at, I wanted to talk about the basketball court first. So let's, hold on, I'm going to add in, let's see. Sorry, I had, yeah, this is what I gotta do. There it is. Just so I can draw on it. All right, so let's look at the bottom one first. These are the lines on a basketball court. This is like, it takes less time to answer the question than it does to set it all up. But let's imagine that you are the person who draws the lines on the basketball court. You have like your little thing that you drive around that draws the lines on the floor. And obviously, that guy wants to draw the lines all in one go without running over the same spot twice. It would be ideal if you could just drive all the lines at once without repeating any portions. Now, this, I think it becomes obvious what you should do. You should think of these lines as making up a graph, which they kind of already do make up a graph. Can anybody say, just by looking, is it going to be possible to draw all the lines in one go, whether in a circuit or in a path? Somebody says no. Why not? Can you say? Yeah, I see actually a lot of junction points with odd numbers. Like up here, there's 3. You would think about the degrees. Actually, there's a lot of 3s, which means that is not going to be possible. I think maybe the rest of them are even that I didn't label, but that's way too many odds in order to do this. So the moral of the story is you can amaze your friends with this knowledge. You can't draw the lines on a basketball court all in one go. Without repeats. Probably the guy who draws the lines actually would even better want to do them in a circuit so that you end up where you started, which is like at the side of the court. You don't want to end up in the middle somewhere. But actually none of that is possible for drawing the lines on a basketball court. All right? Bad news, I guess, for the line drawing guy. I don't know if they really care about this. What about this? So this one is the Pac-Man board. Maybe you can guess what I'm going to ask. I hope you all are familiar with. This is Pac-Man here. My color, I inverted the colors because usual Pac-Man is black background. I hope that you can see all right on the screen. This little guy here is Pac-Man, and Pac-Man's goal is to eat all the little dots by just you walk over them. And you have to avoid the ghosts. They try to eat you. Under certain conditions, Pac-Man can eat the ghosts too, but we don't need to get into that. The question is, can you eat up all the dots without retracing any steps? This would be like the best case scenario if you could just go around the whole thing, eat up the dots without ever revisiting any of the areas that you've been to before, because that's just like wasting your time. Again, the answer is fairly obvious once you know how to look at it correctly. I believe you should try to turn this into a graph. Now, it's not exactly a graph as written, but I would like to consider only the dots that Pac-Man wants to eat and make that into a graph. So maybe I will just scribble on top of this. The graph goes like this, right? I'm just drawing on top of the dots. This is the graph where Pac-Man wants to walk. And the question is, can you actually walk that whole graph without revisiting any place that you've been to before? This would be the best possible Pac-Man strategy, would be to walk everything without any revisitations, right? Actually, you can see because of these little dead ends, actually it's not possible to walk without revisiting anything. But even without those, you can see, again, many intersections with degree 3 here. And this means that's not possible. And I think, I imagine that the people who created Pac-Man specifically did it this way so that you couldn't just walk in one way. It's a more boring game if there was somehow like one perfect way that you should always go. That doesn't make for a very interesting game. So I will say not possible without revisiting sections. It's true. All right. I think that